These are the rest of the notes for Wednesday, and we're still in 2.1, but we're going to continue our discussion of rates of change. So, first of all, the average rate of change of a line, as you can remember from algebra, is really its slope. So, when we're talking about just lines, and I'm talking about, well, what's the average rate of change? And maybe this line right here that I just drew represents, along the x-axis, maybe I have weeks, and along the y-axis maybe I have money. And everywhere along that line, when I go up and over, up and over, up and over, I've got a constant rate of change in how much money I'm earning per week. Maybe I'm getting, maybe it goes up 10 over 1. That would be $10 gaining every week. And if I do that consistently, I've got what's called a linear function. That rate of change is constantly the same. Now, when we're talking about curves or functions that aren't linear, then we're talking about a little different thing when we're talking about the average rate of change. Because graphically, I'm going to draw the picture first before I explain it. So suppose I've got some function that kind of looks like this, and it'll tie in later. We're going to show kind of map out Usain Bolt's 100-meter dash, and you'll know that his rate of change while he's running is not constant. It's not linear. He starts off a little slower, and then in the middle or towards the end he probably peaks, and then he's probably maybe a little slower at the end. And when we talk about average rate of change of a function that's not a line, it's simply going to be, when we take an interval here, let's say maybe it goes from A, so I'm looking right here at A, f of A. I'm going to write that as a point. And then maybe over here, I'm going to take along here, maybe we call that at some B, comma, f of B. When I'm talking about the average rate of change, I know it's kind of going up faster here and then it dips down and ends up over here. It kind of be like if you're driving your car, your average speed. It's the slope of the line connecting the two, which is called our secant line. Slope of the secant line that gives us our average rate of change over that interval. Now again, there's a huge difference between average rate of change and instantaneous rate of change. And you're going to learn a lot about that in physics. I'm going to kind of clean this up a little bit. Instantaneously right here, the rate of change is much greater. Again, if that was a car, I'm going a lot faster right here than I am over here. You know, my rate of change or my slope right here is less positive. So, and even right here, my slope's negative. What that means is my rate of change is going down. But what I've got over the interval, this gives me that average. It's kind of like a car trip where, if you go 100 miles in 2 hours, they say your average is 50 miles per hour. But that doesn't mean that's what you're going the whole time. It's just over that interval. So really graphically, when it says average rate of change, this is really important that we're doing the slope of the secant line. And I'm going to show you that as it shows up in AP tests in the past. I believe this was last year's. I think this is the 2012 first question, or part of one of the questions. First question, part A, and it's a very easy concept. It's a lot of words. So what we've got right here is some water in a tub being modeled by a strictly increasing function. You can see that temperature is going up constantly. It's not going up at the same rate. You can see right in here it went up only about 2 degrees, where over here it went up, about 6, and over here, it's back to only about 1 degree. So we don't have a constant rate of change. That would not make a line if I were to graph it. And it just says right here that it starts off at 55 degrees. They're heating it for 30 minutes, which is why I have an overall increase in temperature. And they give the table of where they've taken the temperature at different intervals along the heating period. And part A just simply says use the data in the table to estimate, and you really need to know what this is asking you. This represents the derivative, which is the slope of the tangent line, but really in real world what that means is the rate of change. It means it wants you to find that instantaneous rate of change okay, which is degrees per minute at 12 minutes. Well, you go to the chart and you're like, well, they didn't tell me what it is at 12 minutes. Well, that's why it says estimate. They want you to give an estimate. So what you do is you go immediately to the right of it and to the left of it. And you assume that it's, it's going like this, but if you go right to the left and right to the right and you do the slope, you'll be really close to that instantaneous rate of change. So really what this is asking you to do is find the slope of the secant line connecting these, and it'll be a good estimate for the derivative. So what we do is we say, well, good estimate of the temperature, rate of change of temperature after 12 minutes would be about my rate of change between these neighbors right here. So best thing for me to do would be to say, well, what happened at W of 15 at 15 minutes? What happened, or what was the temperature at 9 minutes? And then that's over basically a 3-minute interval. But really what I'm doing is the slope of the secant line. If I were to write them in terms of points, it'd be 15, 67.9, and 9 minutes, 61.8. So all I really need to do is find the slope of that. And we know slope is change in y over change in x. And I'll have a good approximation. Again, there's a key word in here that says to estimate it. You don't know exactly what happened at 12 minutes, but you can assume it's kind of the average of what happened in between these. So you would just go to your calculator and say 67.9 minus 61.8 over 15 minus 9, which is 3. And you calculate that out, and I'm not going to go to my calculator right now. And it says, interpret your meaning. This is very important. What does this mean? Okay, when I get my answer, what is this on the top? Okay, that is my degrees. And a fraction always means per. A rate of change is always like miles per hour, or degrees, in this case, degrees per minute. Okay, so what that gives me is my average rate of change. And I'm using that to approximate what happens at 12 minutes. Now again, I'm going to do another one of those so you can see this happening on another one. Again, this is number 2 off the 2011 AP free response question. Same type though, you can see this is kind of a common theme with them. I didn't put parts B and part C on here, obviously, because we don't know enough to answer them yet. But we can answer the first question. It says we've got a pot of tea cooling, so we'd call this a decreasing function. However, it's not linear. It's going down 6, and then we're down 8, and then right here only down 1. So it is constantly decreasing, but not at the same rate. So that's not a linear function. So it says we're doing it from 0 to 10 minutes. T is minutes, H of T is in degrees Celsius, etc., etc. It says use the table on the table to approximate the rate. Rate is a key word for you. Rate means per, rate means slope, all right, at which the temperature of the tea is changing at 3.5. And again, it says to approximate that. So I am looking for the rate of change at 3.5. What is that? What is the slope at 3.5? I don't know. It's not on here. So again, what I do is I make myself an estimate to approximate it. I find the average rate of change between these 2 points, or the slope of that secant line. So again, you could write them as points that at 5 minutes the temperature is 52 degrees, and at 2 minutes the temperature was 60 degrees. And again, when you do your you might even want to write them in order chronologically here if we wanted to be really picky, but when you do your change in y over change in x, which is really, your h of 2 minus your h of 5, if you were going to show your work properly, what's the change in degrees right here? And what's the change in time? All right, so, and you could do it either way. It doesn't matter whether my negative ends up on the top or the bottom here, but I've got, sorry, I've got something in my eye here. So I've got 60 minus 58 over, and again, it's really just change in y over change in x. So I end up with what, 2 negative 2/3. What this is, though, in terms of a label, is this is giving me the rate of change at 3.5 minutes. It's going down about negative 0.667. You're supposed to round to 3 decimal places, degrees Celsius per minute. The average rate of change. All right, so that's kind of it. We're going to come in tomorrow and talk some more. The key to the worksheet is going to be online because there's some tricky stuff in there. So last thing I really want to make sure you understand, I'm going to go through a fake function on here. And I'm going to go like this, and I just kind of want you to watch what's going on right here. So here's my function. It doesn't matter what it is. And I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'm going to label these 3, 4, 5, 6, 7, 8, 9, 10. Just so you know notation-wise what they're looking for. If I just say, what's f of 3? I just want to know the y value at 3. What is this y value? And if that was 1, 2, 3, 4, 5 up, I would say it's 5. So make sure you're really clear with that function notation. Okay? Now if I said, what's f prime at 5? Oops, sorry, that doesn't look very good. If I say what's f prime at 5, remember this is the derivative. I'm asking what's the slope of the tangent line at 5. So you'd go to 5, and you'd go like this, and I'm asking you for the slope of that line, which right now you could only estimate. You know, it's positive for sure, maybe about 1. You know, you can kind of estimate it off the graph. And if I were to say, where is f prime of x equal to 0? I'm asking you, where's the slope of the tangent line equal to 0? Lots of answers to that. Right here, the slope is 0. Right here, right here, right here, right here. So I have multiple places where the slope of the tangent line, or the derivative of my function, is 0. Last up, if I were to ask you for the average rate of change from 4, I'm going to go do that in black, average rate of change from 4 to 6. You go to 4, you go to 6, and although it's not constant, you know, I'm increasing slightly and then less, the average is represented by the slope of the secant line. So if I were to do it from 4 to 6, again, I'd have 4, whatever the y value is at 4, and over here I'd have 6, and whatever the y value is at 6. The slope of this secant line is my average rate of change. So that would be f of 6 minus f of 4, slope, change in y over change in x, over 6 minus 4. So there's a big difference between instantaneous, which is what's happening right here, which is your derivative, of the slope of the tangent line, which is the derivative, versus what's the average rate of change, which basically means, again, what's happening on average between 2 points on an interval. That's just the secant line. So I think if you try that worksheet and then look at the key on Edmodo, I think that'll be a really good process for you, but try to do them on your own. So the homework is the worksheet with the couple from the book that are on your green sheet. And again, I'm going to post the key for that on Edmodo. So there's the end of the notes, and you guys have a great night.